Welcome! In this presentation, we'll tackle LeetCode problem number 1368, minimum cost to make at least one valid path in a grid. This problem is a fascinating challenge that combines graph traversal and optimization techniques. Let's dive in and explore the solution step by step. In this problem, you're given an MXN grid where each cell contains an arrow indicating a direction. The arrow can point in four possible directions: right, left, down, or up. These directions are represented by the numbers 1 through 4. Starting from the top left corner of the grid, your goal is to determine the minimum cost required to make at least one valid path to the bottom right corner. A path is considered valid if you can move from cell to cell by following the arrows without changing direction. However, if you need to move in a direction different from the arrow's direction, you can do so by incurring a cost of 1 for changing the arrow. You also have the flexibility to move to any adjacent cell, regardless of the arrow direction, by paying this cost. The challenge is to minimize the total cost of adjustments needed to create at least one valid path. The output of the problem is a single integer, which represents the minimum cost required to create a valid path from the top left corner of the grid to the bottom right corner. To help clarify, let's look at some examples. In the first example, the input grid is a 3x3 matrix where the arrows are arranged as shown. Following the arrows, we can move to the right from cell 1, 1 to 1, 2, and then to 1, 3. At 1, 3, the arrow points right, but to continue towards the bottom right corner, we must move down to 2, 3. This requires changing the arrow at 1, 3, which incurs a cost of 1. From here, the arrows guide us correctly to the destination at 3, 3, without any additional cost. The total cost to create a valid path is therefore 1. In the second example, the grid layout leads to a slightly higher cost. Starting at 1, 1, the arrow initially points right, so we move to 1, 2, and then to 1, 3. At 1, 3, the arrow points down, which aligns with our intended direction of moving to 2, 3. However, at 2, 3, the arrow points left, but we need to move down to reach 3, 3. To do this, we change the arrow at 2, 3, incurring a cost of 1. Finally, at 3, 3, the arrow points up, so we change it to point in the desired direction, which adds another cost of 1. The total cost for this path is 2. For the third example, the grid contains only one cell. Since no movement is needed, there is no need to change any arrows, and the cost is simply 0. This illustrates the base case where the grid has a single cell, making the solution straightforward. Larger grids require a more calculated approach to minimize the cost, as we saw in the earlier examples. To summarize, the constraints of the problem ensure that the size of the grid can be as large as 100 by 100, which means there can be up to 10,000 cells. Each cell's arrow can only be one of the four possible directions, and changing a direction always costs 1. Some edge cases to keep in mind include grids where no movement is needed, grids where all arrows already align with the shortest path, and grids where most arrows point incorrectly, requiring significant changes. Additionally, when there are multiple valid paths, the goal is always to find the one with the minimum cost. Understanding these scenarios will help you design an efficient solution to the problem. To solve this problem, our goal is to determine the minimum cost needed to modify the arrows in a grid so that there exists at least one valid path from the top left corner to the bottom right corner. This can be framed as a shortest path problem with weighted edges, where the weights depend on whether we follow the arrow's directions or deviate from them. One straightforward approach is to use exhaustive BFS or DFS to explore all possible paths. In this method, we start from the top left corner and explore every path to the bottom right corner, modifying arrows as necessary and tracking the cost of these modifications. However, this approach is computationally expensive. Since the grid can have up to 10,000 cells, the exponential growth in the number of paths makes this method infeasible. While it may provide intuition, its complexity means it's not practical for large grids. A more efficient solution is the 0 to 1 BFS approach. Here, we model the grid as a graph where each cell is a node, and the edges between nodes carry weights of 0 or 1. If we move in the direction of an arrow, the edge weight is 0, while deviating from the arrow adds a cost of 1. Using 0 to 1 BFS, we can prioritize low-cost edges. This is done by employing a deque. When moving along an arrow, we add the next cell to the front of the deque with a cost of 0. If we deviate, we add the next cell to the back of the deque with a cost of 1. This ensures that lower-cost paths are explored first, minimizing the overall cost. The time complexity of this approach is O(m*n), where m and n are the grid dimensions. Each cell and its edges are processed at most once. Compared to Dijkstra's algorithm, 0 to 1 BFS is faster for this problem because most edge weights are 0, making it the preferred choice for efficiency and simplicity. The 0 to 1 BFS method is the chosen strategy for solving this problem. The key insight here is recognizing that the grid structure allows us to treat it as a graph with 0/1 edge weights, enabling us to prioritize zero-cost paths effectively. This approach minimizes the cost without the need to explore unnecessary paths. Additionally, it is faster and simpler to implement than Dijkstra's algorithm, which, while valid, involves additional overhead due to its reliance on a priority queue. In contrast, brute force methods, though conceptually simple, are computationally prohibitive due to the exponential number of paths they need to explore. Overall, 0 to 1 BFS strikes the perfect balance between computational efficiency, conceptual clarity, and implementation simplicity, making it the optimal choice for tackling this problem. The problem we're solving asks us to find the minimum cost to modify a grid in such a way that at least one valid path exists from the top left corner to the bottom right corner. The grid cells contain arrows that indicate movement directions. Moving in the direction of an arrow has no cost, but moving against the arrow incurs a cost of 1. This setup essentially translates the grid into a weighted graph, where each cell represents a node, and arrows define directed edges with weights of either 0 or 1. To solve this, we'll employ the 0 to 1 breadth-first search algorithm, which is an efficient method for finding the shortest path when edge weights are binary. The key idea is to use a specialized BFS with a deque to prioritize exploring zero-cost moves first, ensuring we find the minimum cost path efficiently. Let's break this approach into clear steps to understand it better. First, we'll model the grid as a graph, with each arrow direction defining weighted edges. Then, we'll map the directions explicitly and implement the BFS traversal to explore paths, minimizing the cost as we go. To implement this, we begin by mapping the directions represented by arrows in the grid to their respective movements. For example, an arrow pointing right corresponds to moving one step to the right in the grid, and so on for left, down, and up. Each arrow in the grid is associated with these predefined directional movements. Once we've established this mapping, we can compute the cost to move from any given cell to its neighboring cells. If the direction of movement aligns with the arrow in the current cell, the cost is 0. Otherwise, moving against the arrow adds a cost of 1. With this cost model in place, we initialize the BFS by starting at the top left corner, 0, 0, with an initial cost of 0. A visited matrix helps us track the minimum cost to reach each cell, ensuring that we only process a cell if the current cost to reach it is better than any previously recorded cost. As we traverse the grid, we evaluate all neighboring cells, updating their costs and adding them to the deque. Zero-cost moves are prioritized by placing them at the front of the deque, while moves with a cost of 1 are added to the back. This ensures optimal exploration of the grid. There are some important insights that make this approach efficient and effective. First, the use of 0 to 1 BFS significantly optimizes the algorithm compared to traditional Dijkstra's algorithm. By leveraging a deque, we avoid the overhead of maintaining a priority queue, which is unnecessary when edge weights are limited to 0 and 1. Additionally, the grid is represented implicitly as a graph, meaning we don't need to explicitly construct edges, which saves both time and space. Another key optimization is the algorithm's ability to terminate early. Since we process cells in order of increasing cost, the first time we reach the target cell, the bottom right corner, it is guaranteed to be with the minimum possible cost. This eliminates the need to continue exploring the grid once the goal is reached. To implement this efficiently, we rely on 3 core data structures. The deque facilitates the 0 to 1 BFS traversal. The visited matrix stores the minimum cost to reach each cell, ensuring we don't revisit cells unnecessarily. Finally, the direction map provides a simple way to translate arrow values into movement directions, streamlining the cost calculations during traversal. Now let's analyze the computational complexity of this algorithm. In terms of time complexity, we process each cell in the grid exactly once, and for each cell, we evaluate all of its neighbors. This results in a time complexity of O, m*n, where m and n are the dimensions of the grid. For space complexity, we use the visited matrix and the DEEC to store intermediate data during the BFS traversal. Both of these data structures require O, m*n, space, as they scale with the size of the grid. Let's now walk through the pseudocode to see how these concepts are implemented. We start by initializing the grid dimensions, direction mappings, the visited matrix, and the DEEC. The DEEC is seeded with the starting position, 0, 0, and an initial cost of 0. As long as the DEEC is not empty, we repeatedly dequeue the front element to process the current cell. If the current cell is the target cell, we return the associated cost, as it represents the minimum cost to reach the bottom right corner. Otherwise, we proceed to explore all valid neighbors of the current cell. For each neighboring cell, we calculate the new cost based on whether the direction of movement aligns with the arrow in the current cell. If the movement matches the arrow, the cost remains unchanged. If it doesn't, we increment the cost by 1. If this new cost is lower than the previously recorded cost for the neighbor in the visited matrix, we update the matrix and add the neighbor to the DEEC. Zero-cost moves are added to the front of the DEEC to prioritize them, while moves with a cost of 1 are appended to the back. This ensures that the BFS explores paths in order of increasing cost. Once the DEEC is exhausted, if we haven't reached the target cell, we return -1 to indicate that no valid path exists. This implementation efficiently calculates the minimum cost to create a valid path in the grid, leveraging the 0 to 1 BFS technique and the specific structure of the problem. Here, we start by importing the required modules and defining our min-cost function within a solution class. The function takes a grid as input, representing the board with arrows indicating directions. First, we determine the number of rows and columns in the grid and define a list of possible movement directions: right, left, down, and up. These are represented as coordinate changes in the directions list. Next, we initialize a DEEC to act as a priority queue for our 0 to 1 breadth first search. This DEEC starts with a tuple representing the initial position in the grid, 0, 0, and a starting cost of 0. We also create a visited matrix to keep track of the minimum cost required to reach each grid cell, initializing all values to infinity except the starting cell, which is set to 0. Now, we enter a while loop that continues processing as long as there are elements in the DEEC. At each step, we pop the leftmost element, representing the current cell and its associated cost. If this cell is the bottom right corner of the grid, we return the current cost, as we've successfully found the minimum cost to reach the destination. Otherwise, we iterate through all 4 possible movement directions. For each direction, we calculate the new potential position by adding the direction offsets to the current cell's coordinates. We check if the new position is within the grid boundaries to avoid invalid moves. Next, we determine the cost of moving to this new cell. If the direction aligns with the arrow in the current cell, the move has no additional cost, otherwise, we add 1 to the cost. Now, if the newly calculated cost is less than the previously recorded cost for this cell in the visited matrix, we update the cost for this cell in the visited array. Depending on whether the move incurred additional cost, we either append the new state to the front of the DEEC for priority or to the end for less urgent processing. This ensures that no-cost moves are prioritized during our BFS traversal. Finally, if we exhaust all possibilities and cannot reach the bottom right corner, we return -1, though this scenario should never occur for a valid grid. This implementation efficiently finds the minimum cost path using the 0 to 1 BFS algorithm, ensuring optimal performance even for large grids. Here, we begin by importing the necessary libraries and defining the solution class. The method minCost takes a 2D grid as input, where each cell specifies a direction to move. First, we determine the grid dimensions and define an array of directions representing right, left, down, and up movements. These directions will help us navigate the grid. Next, we initialize a DEEC to implement a 0 to 1 breadth first search, which is efficient for problems involving weighted graphs with costs of 0 or 1. We also create a visited matrix to track the minimum cost of reaching each cell, initializing all cells with the maximum possible value except for the starting cell at the top left corner, which starts with a cost of 0. The DEEC is seeded with the starting position, represented as cost, x, y. Now, we enter the main loop, where we process each cell in the deque. We extract the current cost and position, and if the bottom right corner is reached, we return the cost, as it represents the minimum cost to complete the path. Next, we iterate through each possible direction to determine the neighboring cells. For each direction, we calculate the new coordinates, ensuring they remain within the grid boundaries. We then compute the new cost to move to this neighbor. If the direction indicated by the grid matches the current direction, the move is free, so the cost remains unchanged. Otherwise, we add 1 to the cost. If this newly calculated cost is less than the cost recorded in the visited matrix for the neighbor, we update it and decide where to place the neighbor in the deque. If the move has no additional cost, the neighbor is added to the front of the deque to prioritize it. Otherwise, it's added to the back, ensuring costlier moves are processed later. Finally, if the loop finishes without finding a solution, which shouldn't happen for valid grids, we return -1 as a fallback. This implementation efficiently calculates the minimum cost using the 0 to 1 BFS approach. To solve this problem, we start by initializing the key components of our algorithm. The grid dimensions are determined as 2 rows and 2 columns. We define the directions for movement: right, left, down, and up. Then, we initialize a priority queue with the starting position at the top left corner, 0, 0, and a cost of 0. Additionally, we use a visited matrix to track the minimum cost to reach each cell, starting with 0 for the top left and infinity for all other cells. As we process the first cell, 0, 0, we explore its neighbors. Moving right to 0, 1 aligns with the arrow direction, so no additional cost is incurred. We update the cost 4, 0, 1 to 0 and add it to the queue. Moving down to 1, 0 requires changing the arrow direction, adding a cost of 1. We update the cost 4, 1, 0 to 1 and add it to the queue as well. At this stage, the queue contains the positions 0, 1, and 1, 0. Next, we process the cell 0, 1, which has a cost of 0. From here, moving down to 1, 1 aligns with the arrow direction, so no additional cost is incurred. We update the cost 4, 1, 1 to 0 and add it to the queue. Now we process the cell 1, 1, which also has a cost of 0. Since this is the bottom right corner of the grid, we have reached our goal, and the minimum cost is 0. This simple example demonstrates how the algorithm prioritizes paths with the lowest cost first, taking advantage of the grid's arrow directions to minimize adjustments. Now, let's consider a larger grid where direction changes are more frequent. The grid is 3 rows by 3 columns. We initialize the queue with the starting position 0, 0, and cost 0, and the visited matrix is set up with infinity for all cells except the starting point. From 0, 0 moving right to 0, 1 aligns with the arrow direction, so no cost is added. We update the cost 4, 0, 1 to 0 and add it to the queue. Moving down to 1, 0 requires changing the arrow direction, adding a cost of 1. We update the cost 4, 1, 0 to 1 and add it to the queue. Next, we process 0, 1, exploring its neighbors. Moving down to 1, 1 requires a direction change, adding a cost of 1. We update the cost 4, 1, 1 to 1 and add it to the queue. From 0, 1, we also explore moving right to 0, 2. This move requires a direction change, so the cost is 1. We update the cost 4, 0, 2 to 1 and add it to the queue. At this point, the queue contains several positions, including 1, 0, 1, 1, and 0, 2. The algorithm continues to process these positions, exploring their neighbors and updating the costs dynamically. By using the 0 to 1 BFS approach, we ensure that the priority queue always processes the lowest cost paths first. Eventually, after exploring all necessary positions, we find that the minimum cost to reach the bottom right corner, 2, 2, is 2. This example illustrates how the algorithm handles larger grids and efficiently navigates through required direction changes. In all cases, the 0 to 1 BFS algorithm ensures that paths with 0 additional cost are processed first, guaranteeing that the minimum cost is found efficiently. By prioritizing movements that align with the arrow directions and only adding costs when direction changes are necessary, the algorithm is both optimal and fast. This approach is highly effective for grids of any size, including edge cases like single-cell grids, where the cost is naturally zero since no movement is required. The use of a priority queue in a visited matrix ensures that each cell is processed at most once with the minimum cost, making this solution both time and space efficient. To analyze the time complexity of our solution, let's start by considering the grid exploration process. The algorithm employs a 0 to 1 breadth-first search, or BFS, to traverse the grid. Since the grid has dimensions of rows x calls, the total number of cells it needs to explore is simply rows * calls. Now, for each cell, the algorithm evaluates up to 4 potential neighbors corresponding to the 4 possible movement directions. Thanks to the 0 to 1 BFS approach, each cell is added to the deque at most twice, once when the movement direction matches the arrow direction, and again when it doesn't. This results in a maximum of 2 rows calls deque operations. Additionally, for each deque operation, the algorithm checks all 4 possible neighbors, leading to 4 2 rows calls direction checks in the worst case. Since these operations dominate the runtime, the overall time complexity is proportional to O rows calls. The space complexity of the algorithm can also be analyzed by breaking it into its components. First, the algorithm uses a visited 2D array to store the minimum cost for reaching each cell. This array has dimensions of rows x calls, consuming O rows calls space. Second, the deque, which stores tuples containing the cost and coordinates of cells, grows linearly with the number of cells. In the worst case, all cells might be added to the deque at least once, requiring an additional O rows calls space. Finally, there's some auxiliary space used for constants like the directions list and local variables, but this is negligible and does not affect the overall complexity. When we combine these components, the space complexity remains O rows calls. Now, let's examine the algorithm under different scenarios to better understand its behavior. In the best case, if the grid's arrows are perfectly aligned with the shortest path from the top left to the bottom right corner, the algorithm performs a single BFS traversal with minimal deque operations. Despite this optimal alignment, the time complexity is still O rows calls, since all cells must be processed. In the average case, such as with a randomly generated grid, the algorithm explores multiple paths with varying costs, requiring more deque operations. However, the complexity remains bounded at O rows calls. Finally, in the worst case, where none of the arrows align with the shortest path, every cell is processed twice, once with cost 0 and once with cost 1. Even in this scenario, the algorithm's efficiency holds, maintaining a time and space complexity of O rows calls. Compared to a naive approach that explores all possible paths with exponential complexity, the optimized 0 to 1 BFS approach is far more efficient and scalable. To solidify our understanding, let's break down the mathematical reasoning behind the O rows calls complexity. The grid contains rows calls cells, and each cell is added to the deque at most twice during the traversal. This results in 2 rows calls deque operations. For every deque operation, the algorithm performs up to 4 neighbor checks. Therefore, the total number of neighbor checks is bounded by 4 2 rows calls. Since both the deque operations and neighbor checks scale linearly with the number of cells, the overall time complexity is O rows calls. Similarly, the space complexity is linear because the visited array and deque grow proportionally to the grid size. This linear behavior ensures the algorithm is both time efficient and memory efficient for large grids. When solving this problem, there are a few common mistakes to watch out for. First, many assume that a simple breadth-first search without considering costs will work, but this is not the case. Since the objective is to minimize the cost, you need to ensure that lower-cost paths are processed first. This means using a priority queue or deque, rather than a basic queue, to handle the traversal efficiently. Next, it's easy to overlook edge cases. For example, grids with only one cell, scenarios where no arrows need to be changed, or cases where all arrows point away from the target can lead to bugs if not properly tested. Another frequent issue is getting the direction mapping wrong. The problem clearly defines the arrow directions, and confusing these, such as mapping one to up instead of right, will result in incorrect traversal. Finally, relying on depth-first search for cost minimization is another mistake. DFS is not designed for finding the shortest path in weighted graphs, as it doesn't guarantee optimal solutions and can waste time exploring suboptimal paths first. Now, when implementing a solution, choosing the right data structures is critical. Using inefficient structures, like a basic list instead of a priority queue, can significantly slow down your program, especially for larger grids. Additionally, understanding the underlying algorithmic patterns in this problem can make a big difference. This is essentially a variation of shortest path algorithms, such as Dijkstra's or 0 to 1 BFS. Recognizing this early can guide you toward the right approach. The grid traversal and direction changes resemble weighted graph traversal problems, so familiarity with these algorithms is essential. It's also important to focus on optimization. For instance, using a DEEC for 0 to 1 BFS is often faster than a priority queue due to reduced overhead. And during interviews, your communication matters just as much as your code. Clearly explaining how you handle direction mapping and cost updates will show a structured and thoughtful approach to solving the problem. There are several related problems that can help deepen your understanding of this topic. For example, LeetCode number 743, network delay time, is another weighted graph traversal problem that uses Dijkstra's algorithm. Similarly, LeetCode number 505, the maze 2, involves finding a shortest path in a grid, but with an interesting twist, it uses rolling ball mechanics. Another relevant problem is LeetCode number 1293, shortest path in a grid with obstacles elimination. This problem combines grid traversal with constraints on the number of obstacles you can eliminate, which is quite similar to the direction change constraints in this problem. Finally, LeetCode number 787, cheapest flights within K-stops, focuses on cost minimization in a graph while adhering to specific constraints, making it another useful example for understanding how to approach cost-based traversal problems. There are also alternative approaches to solving this problem, each with its own trade-offs. One efficient method is 0 to 1 BFS, where you use a DEEC to prioritize zero-cost direction changes while adding one-cost modifications to the back of the DEEC. This approach is faster than Dijkstra's for this problem because it avoids the overhead of managing a priority queue. Another option is Dijkstra's algorithm, which uses a priority queue to always select the path with the lowest cost at each step. While it's slightly slower than 0 to 1 BFS due to heap operations, it is easier to implement and widely applicable to other shortest path problems. Lastly, there's the brute force approach, where you explore all possible paths and calculate the cost for each. However, this method is computationally expensive, with exponential complexity, and is not suitable for larger grids. Understanding these approaches and their trade-offs is key to choosing the best solution based on the problem constraints. Great job sticking through to the end. To recap, we used a shortest path algorithm to solve this problem efficiently. Remember the importance of optimizing pathfinding in grid-based scenarios. Don't forget to practice similar problems to reinforce your understanding. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!